Today we're live coding again, and we're live coding on an open source project called Studio, which is something that's just kind of become usable recently and that we're developing very actively. The Studio is a debugger for application data. So the idea is that you often have complex applications that generate complex data structures, often as internal state, and in order to understand and debug those applications, it's very handy to have some tooling that can make sense of their internal data structures and kind of present them to you in a way that you can analyze and troubleshoot. So today what we're actually doing is extending Studio to debug itself in a certain sense. So Studio is written in two parts. The front end part is a Pharo Smalltalk graphical application, and the back end part is a Nix API, which specifies how to go out and produce data that needs to be inspected and to pre-process it. So the overall workflow is that you open up the user interface, you write a Nix expression to say what it is that you want to inspect, and then that goes off and it builds your data to inspect, which could be downloading it from a continuous integration server, it could be fetching it from a file, it could be actually running an application in order to produce new data, and then it can do any pre-processing using any tools that you need to make it easy to interpret by the front end. So today we're actually following from what we did in the last stream, which was to start writing some code that doesn't just call out to Nix as a command to make things happen, but also starts to peek into the internal data structures that Nix maintains in a directory called /nix/store. And this is actually a very Studio-like thing to do. The whole idea is to actually be a little bit like a kind of an X-ray vision into an application and see what it's doing internally. So it's not that radical actually to bypass Nix and start looking at its files internally. And what we want to do now, we already wrote a parser for understanding the basic structure of a Nix store derivation, which is a description of something that needs to be built, or that can be built, and all of its dependencies as a graph. We're parsing that now, and the next step is to actually do something with the data after we parse it. And I think what I'd like to do today is a couple of visualizations. One is a kind of a graph to see a dependency graph to get a feeling for how something gets built, and which parts of it have already been built, which parts of it are currently building, and which parts of it need to be built and are blocked by dependencies. And then I'd also like to have a kind of a tree view of this, is my thinking. So let's hop in and we'll look at some existing Studio visualizations first as a kind of a template or an inspiration for what we want to do with the Nix code. And we'll use this both like as a visual inspiration and also for code, because I haven't written Pharo UI stuff in a little while, some months perhaps, so it'll be handy to refer to some code that I wrote earlier. So we'll pull that up to start with. So let's do that. Here is the same Pharo image that we were working in last time around. Actually has a bunch of code that we haven't checked in, pushed anywhere, so we're just gonna get these visualizations working before we kind of package that up and put it onto GitHub. So first off, let us open the Studio interface as you would normally see it as a user. Oops, we'll open the Studio Inspector. And the application that we have the best support for today is Raptorjit. So if we would say raptorjit.run, this is a Nix expression, and we're going to give it a string which is going to be Lua code, which is going to run in the Raptorjit virtual machine, and then we're going to see an inspection of the result of that. So if we would say for I is 1 to the big number, do nothing. We just run a really simple script just as an example to see Studio pulling in some data. And okay, and here's a little table view. So this is one of the views I would like to get on the Nix store actually, although I would like to have it as a tree. We have some things that can appear as a tree, not in that simple example. Let's go to a visualization then. This is a visualization in the Smalltalk environment with a toolkit called the Agile Visualization Toolkit, which is pretty neat. So I'd like to build something vaguely inspired by this to show the dependency graph for Nix packages. So if we say that we want to run a Raptorjit program with Nix, for example, I'd like to get a visualization looking something like this that says, well, we need to run a Raptorjit program. To do that, we need to build the Raptorjit virtual machine. To do that, we need to have a Lua to bootstrap from. We need to have GCC and so on, and just see the dependency tree. It's one of the things I would like to do. And then I'd also like to get a table view, and just to be concrete about that, let's find in here, let's find an example. I want to find a C object. Because I've already added kind of extensive support for looking at raw C objects using dwarf debug information, and that's kind of similar to the way the next door support will work visually in any case. So I'm going to just write a little bit of Smalltalk code to try and find a GC trace. Just try and find an example of a C object that we can inspect. We'll refer back to. We have a GC trace object, dwarf value, see that as dwarf. Oh no, there's a bug in that. Oh, that's too bad. Let me instead then pull up an example from the manual. So fixing that bug is not quite our agenda right now. We won't get sidetracked by that, but it'll be interesting to come back and look at. Meanwhile, we have a manual that is actually automatically built from CI. And we have somewhere here no, I don't have the dwarf example in the manual anymore either. Oh well. I'm going to look very briefly at whether that was something. Oh, this is something we've already fixed. So we might be basing this. The version that we're developing on might be missing some of the fixes that we have upstream. That was a little careless as a starting point. I'm a bit too lazy to merge that in right now. So I think I kind of remember what the I think I remember what the problem was. Let me just try very briefly to fix. No, bugger that. Never mind dwarf as the example. That's a bug that we've already fixed elsewhere. So we will. Let's make a slightly. We'll start another version actually. We'll just install a fresh studio. Just for the sake of concreteness, we're gonna just pull up the normal Studio UI because I'd like to have this for reference. Run the development version in VNC mode. I mean, that's how you install Studio. You do a git checkout. You do a git clone to get a copy of the source tree. You can optionally do a checkout to get a particular branch and version, and then you tell it to run in VNC mode, and it tells you a VNC endpoint, display number 29 for us. So then we'll start on another machine, on a Mac, a VNC viewer. Pull that over. This is the basic way that Studio runs. I've demonstrated this before, but it's worth repeating. Studio runs on Linux, and my desktop machine here is a Mac. So how do you run a Linux application with a Mac? I just run it on any convenient Linux machine. It could be a Docker VM on the Mac, which is really easy to start. In my case, it's a Linux machine that I have in the basement. It could also be an EC2 machine or a Hetzner server or anything like that. The notion is that you should always pretty easily be able to get access to a Linux machine for development, even if that's not what your desktop is. So let's just try that example again. Raptor run. Run a pretty trivial script. And then we will find trace. And we saw before the visual representation. Now I want to see this as a raw C object. But that's interesting. Okay, so this is a bug that we actually have on the upstream version. So I remember fixing this, but we must not have pulled that fix in anywhere. Something's gone wrong there. So that's very interesting. I'm going to make a note of that. We've got to come back and fix that. Meanwhile, we have the code, for example, we can browse, but we don't have the we don't have it as a visual example to look at right now, which is which is significant. Okay, so we're going to fix, and actually the way that we should fix that is to put it into the manual, because the Studio manual is built automatically by continuous integration, and it actually starts the application and drives the GUI a little bit and takes a screenshot and puts that screenshot in a fully automated way. So kind of the fact that the dwarf viewing support is broken is kind of a symptom of us not having screenshot coverage of it in the manual. So if we have if we just put a screenshot of that into the manual, then we'll see, you know, when the manual builds, whether we have the dwarf support working actually or not. So one step at a time. Anyway, back to where we were. We're gonna start from, first of all, we don't need that new UI that we started. We'll go back to the one that we already had before, and we are going to look at our parser that we wrote before. So can I browse my history of things? No, not in this one. We open a normal workspace. See if we wrote. Here's where we had something we did in the last time. We did not a nix build, but a nix instantiate to generate the derivations to describe how something would be built without building it. We run that, then we get two derivations, one for running a Raptorjet program and another for inspecting the results. And what we did last time, this is a file name here. What we did last time was parse. We wrote a parser for that, and here we go, nix A-term parser. So what does that produce? Okay, sorry, I tried to parse the file name rather than the contents. So actually, if we say self as file reference, we go from a file name to a file. Contents of the file is this. So this is what the definition of a nix derivation looks like, which is not especially pretty. Then if we take that now, browse the contents, and now over here, what we're looking at now is a string in the Smalltalk environment, which contains a nix derivation. Here is a little workspace where we can write code in the context of that object. So self here refers to that string. We create a parser and ask it to parse this string. Seems to have got stuck somehow. Okay, good. So we parse that, and now the parser worked. So I fixed some trivial bugs since the last stream. The parser worked now. So what we got is an object of class nix store derivation. It has outputs, it has input sources, it has a platform, it has a builder. Although we can see that those are not in the right order, actually, come to think of it. So the parse tree doesn't look right. The builder certainly looks suspiciously like a platform, so we might have got the order wrong on those. Have a quick look and see actually what that. So that's platform and builder seem to be reversed. Builder is there, platform is there. That looks more like an environment, right? That looks more like value. So this looks totally wrong. I think we parsed it okay, but then when we unpacked that parse tree, we got everything in the wrong order, which is kind of interesting. We need to, as a first step, we need to actually sort that out. So we had, let me see if I can pull up a pretty printed version here somewhere. There. This is the thing that we parsed with just the white space kind of made a little understandable. So let's look at the order of things in this file compared with the way that we're unpacking them in the Smalltalk code. I'll do a copy paste of that perhaps. So nix store derivation. We browse the class. have a method where we initialize it from an array. And we say that the outputs are the first thing in the array, the input sources are the second, then the platform and the builder and the args and the end. Okay, so does that in any way agree with what we have over here if we put them side by side? The first thing is supposed to be outputs. It looks about right. Then it's supposed to be input sources. What we have there is a list of tuples, of two tuples, where the first element of the tuple is a derivation, the second element is the name of an output from that derivation. So that actually does kind of look like a list of input sources, unless those are the input derivations, but okay, it looks plausible up until now anyway. Then over there we're saying platform, and here it's obviously the builder. So that's a mismatch. What is this? Why is there a reference to bash there? How many elements do we have here? One. Hold on, am I even reading this? No, I've read that wrong. So I'm going to put some extra line breaks in here to try and see where each of the elements actually is. What the elements are that we have. So those are the things that we have, actually. So first element is called out. The four tuple, string out, and the name of basically that's the thing that we're building, and a couple of empty strings. So I'm going to say that actually does look like a set of outputs. We have something called out, but it's a bit tricky. You know, we looked for a specification of this format last time, and we didn't actually find anything very satisfying. So we're kind of a little bit in the dark here. So we might just struggle our way along, kind of figure out what seems plausible. So I think the outputs, that does look plausible, but let's say make the code just a little bit more refactorable. We'll say the S is just say something. No, not as string. I want to not say first, second, third, and so on. I just want to say next, next, next. Let's just see how you do that in Smalltalk. I don't quite remember. We have an array. Is it? We cannot say as string. Can we say read string? Yes. What about if we say self next? Then we get 1. If we run that again, we get 2. If we run that again, we get 3. If we run that again, we get nothing. Okay, good. That's what we want. So I'm going to write it that way instead. We're going to say next, 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 so that we don't have to worry about, so that we can reorder them more easily. Okay, we're kind of satisfied that the first thing we're pulling out is the list of outputs. Plausible anyway. And what have we got? A list where each element is a two-tuple, which is the name of a derivation followed by the name of an output. So just immediately, I'm not sure whether that is. If we look at the names that we had, I'm not sure if that's the input derivations or the input sources. I want to say it's the input derivations, which we were expecting to come last. Okay, for now, we're going to suppose that that's the input derivations. see how this pans out, if you believe it. And this is interesting. I mean, we're live coding, so maybe I would otherwise be tempted to do a bit more Googling and that kind of thing. But, you know, it's for some reason I prefer to actually code when we're doing the live coding. So I err on the side of too much time writing code rather than reading. Just take that as it is. So then have a builder. Was that one of our things? Yes, builder was the next thing. And then that's a platform. And then I don't know what that is. So, I mean, we're referencing bash. This is, I mean, I guess it's the program that's going to run this builder. What would that be called? It doesn't look like the end. Ah, you know, it actually kind of looks like maybe bash is the builder and args is the script got to run. That seems actually at least plausible. Let's try that. Let's try that. Somebody knows Nix better than me. Just pipe in and give me a pointer. Thank you for the live chat comments. I don't know the answer to the questions that are coming. We're gonna have to figure it out as we go along. If anybody wants to Google what a Nix A term actually looks like and tell me, that would also be fine. But I'm gonna struggle on. We're gonna say that this is the builder. The bash is the builder. We're going to say that this default builder.sh is the argument that's going to run, and it's going to figure out how to do the build by looking in the environment. So that's not the builder. That is the args. So what do we have? Yeah, the args, then the platform, then the builder. Oh, but then we have trouble, right? Because that's obviously the args. Minus E. Okay. So actually, I don't know what that is. It's not the args. I'm just put an underscore there because we've got to figure that out. Args is the next thing from the string. And then what do we have? And this looks very much like the environment. These will become environment variables that bash will look in to figure out how to do the build. What were we calling that? Env. So we've given reasonably satisfying names for everything. And so, okay, input sources, that is that's the thing we haven't assigned here. We have one thing that we didn't figure out what it was called. Thank you for that link. I'm gonna pull up this link from the chat now. We'll see if this. Thank you very much. Let's have a look. Well, it didn't come as a link. How do we do that? I'm gonna type in. Well, here we've labeled types. See that. Okay, this is useful actually. So, I mean, here we have a Haskell type definition for the thing that we're parsing, and I don't know if this is in any kind of a strict order, right? Because this doesn't necessarily have to correspond with a file, but it should give us a little bit more type information about each field, and we can then see how that agrees with what we have. So the outputs is supposed to be a map of text and a derivation output. Is what we have. Hang on, we'll actually we'll pause an example of this and then we'll see. Thank you. This was input sources, was that one? So for now, if we just take this as our current version, and now we're going to sanity check how it looks. We're going to run that, sanity check how it looks. So we try again, parse file, and then this is what we got. Doesn't expand so well. Yeah, I'm not sure. It would be really handy to have a really concise tree view for something which is kind of an array of arrays. Maybe I could convert this to, I don't know. Anyway, we could conceivably massage this this Smalltalk object into something that's a little bit easier to browse. Let's have a quick look. Item. Okay, that's semi-okay-ish. Okay, let's just compare this. How's the Haskell here for reference? And what's it telling us? It's telling us the outputs is we're going to assume that when they say map, they're kind of mapping this onto a two-tuple, or onto a tuple. The text and a derivation output. Our outputs are we have a four tuple there, although two of the things are empty. I mean, it's slightly tricky, right? Because what we're looking at here is the internal structure in some Haskell program that also parses things, but we don't know how closely this matches. How close this matches the input. So they only have 2 fields in their outputs, whereas we have 4, but 2 of ours are the empty string. So is it actually because those are meaningless and they've stripped them out, you know, from the external format to the internal one? Seems plausible. Just have a look here. Input sources. It's a set file paths. What does our input sources look like? An array with 1 item, which is a builder. That sounds right. A set. Yeah, that's an array. We only have 1, so it passes the sanity check. Platform looks really sane. Builder. What do we have for builder? We have a string for builder. What do they have for their builder? Yes, text. Args. We have an array of command line arguments. So basically what they have. Environment. Okay, so I'm thinking for now I think we've basically got our basic file structure okay. I think that we've decoded each field and we've assigned them to the right variables, I think, although I'm not 100% sure on all of them. But now if we come back actually to there's a parser there as well. Okay, I think this is good enough for our purposes now, because what we'd like to do actually is just kind of charge forward a little bit, and what we would like to do is get something visual happening, right? So we have one derivation here that we've parsed, and it references some other derivations. It's where do we put it in the end? Input derivations. So I mean, we could go out to the file system and we could kind of spider our way out and recurse through this and load some of those as well. And we might find that some of the references are in common. You know, some of them will kind of they'll fan out and then they might converge. You know, because a lot of things reference Bash, a lot of things reference GCC and so on. And it would be interesting to get a little picture of that. So that's actually what I want to do right now. So we have a next door derivation object. So I'd like to be able to. I'd like to be able to first of all get the names of all of its input derivations. So if we would say self on our, this is code that we're running on our next door derivation. If we say self input derivation. Okay, so this is kind of how you often do things in Smalltalk. We want to have a method called input derivation names. It doesn't exist at the moment, so we just try calling it, and then we get an exception saying this object next door derivation did not understand the message input derivation names. And one of the options we have is to create that. So this is the programming in the debugger model, which is fairly convenient, I think. So we're going to just create that model here in the debugger. Sorry, create that method here in the debugger, and when we have it, then we can ask the debugger to just try again, and we just kind of keep our context on the stack there. So this is going to be an accessing method. Every method has a category, and we're going to get it by taking our input derivations variable, which input derivations, each element is actually two things. It's the name of the file name of the derivation, and then the output from this. So in Nix, you have a single derivation that builds several things, several outputs, and you can pick which one you depend on. For now, we're just going to take the derivation. So actually, all we're going to do is return input derivations collect first. So collect. This is map. So we have a collection, an array called input derivations, and each element of that array is also an array of two elements, and we're going to take the first of those. So this is we're programming a Lisp. This is anyway. I'm not sure that helps anybody. That's what it is anyway. So fine, we're going to run that now, and it worked. So we ran self input derivations, and the result was an array of 4 items, and the items were these strings, each of which is an input derivation. So now it would be quite handy to be able to parse those as well, right? So instead of just getting file names, we would get actual we get the same like parse tree objects. So we return them, and this is going to be a little interesting because when we take a set of dependencies that we want to visualize, we're going to need to be a little bit careful that it might be circular, maybe it can't be circular, I don't know. But in any case, we might visit the same file many times. There might be a lot of derivations that also have a common derivation, and in those cases, we're not going to want to reparse it every time and have separate objects. We're going to want to have the same derivation always represented by the same object, so that when we visualize it, the lines converge. We don't have multiple nodes that all represent the same thing. We want to have one node. We want to have all of the edges lead to that. So at some point, we're going to need to represent a set of derivations, and maybe that time isn't now. Maybe if we is this the smallest step that we can take to define a new abstraction, which is a set of derivations, which would in this case be seeded by this this one that we start with, to just say go out and make a set of every relevant derivation. Yeah, we'll do that. We'll start programming. We'll program first and think later. That's okay. What we're going to do now is make an object that represents a set of derivations, and we're going to populate it by traversing all of the dependencies of some object. When in doubt, code. That's our live streaming philosophy. Our normal programming philosophy is more like when in doubt, take the dog for a walk, or have a little bit of a think, have a cup of tea or something. But that's not what we're doing now, because that's not very social. So let's dig ourselves a hole. So we're going to have a method called self. Let's fix input derivation set. We're going to create a method called input derivation set, and that's going to return a new kind of an object, which is going to represent a set of derivations. So again, we're going to just create this. We just called a method that doesn't exist. The debugger allows us to create it. There's also going to be an accessing method, and what we're going to do is say we're going to declare a local variable set. Say the set is a next or derivation set. New object of that type, and we're say visit to mean, you know, soak up this object. We're gonna give it names. We're gonna say visit. We'll be a little bit explicit, shall we? Do we already have the name of this derivation file? Maybe not. We're gonna have it anyway. We're gonna pretend that we have a variable called instance variable of that name. So this is the way that you program in Smalltalk. You just pretend that you have everything. You got a method you want to call, you just call it, and the debugger pops up. You got a variable you wish that you had, you just reference it, and the debugger will give you the option to define it. So if we now ask to, it'll be interesting to see exactly what happens when we ask the compiler to accept this code. Oh, sorry. At the end, we want to return the set. This is going to be recursive. So, bang. What does it say? First, it says unknown variable next door derivation set. Please correct or cancel. Do we want to define it as a class, or as a global variable, or as a class variable, or what do we want to do? And we want to define this as a class. So we're going to create an object, a class called next door derivation set, and I think the small talky thing would be to make this actually a subclass of set. Let's make sure that's a real concrete class. I think that's what you normally do, right? Like often you would kind of wrap things. Often you would kind of in most languages you don't subclass things like array and set and that kind of thing. Rather, you would create an object that would have a variable which is one of those things. But I don't think that's what you do in Smalltalk. So if we look at the hierarchy, the subclasses of set. There are some subclasses of set, but actually not that many. Okay, so maybe that's a bit advanced. Maybe we will actually just make this an object, and it will have a variable which is the set. That's fine. That's okay. Okay, and then what else? Derivation file name is not defined. We're going to declare this as an instance variable, and we're going to have to initialize that at some point. So at some point we're going to reference that, and we're going to get like a null pointer exception, so to speak. And we'll need to fix that when the time comes. Meanwhile, let's see what happens when we run this. Instance of next door derivation did not understand visit store derivation path. So now we have this input derivation set method, and it creates an object of class next door derivation set that we just defined, and then it asks that to visit derivation path, and that method we haven't written yet. So again, we're just going to, from here, we're going to just create that on the class next door derivation set. So this will be an updating method, not an accessing method. And when we call this now, we use this instance variable that we just defined that didn't have a value, so it actually got like a null value there. But we're going to make this a path. And what are we going to say? We're going to say if this path doesn't exist, then that's an interesting error case, right? If we want to spider out across all of the dependencies, if we reach one that's not there, then I think for now we want to actually make that an error. If you look for the dependencies of something and you can't determine them, we'll let that be an error. So I think we won't write any code to detect if the file doesn't exist. We'll just allow that to give us a kind of a no such file exception. So then what we want to do is just say path as file reference contents. That's going to turn it into, it's going to give us a string with the contents of the file. And, well, no, first we want to see if we've already been there. So this is going to be called potentially many times on the same path. So actually we need to have we need to have a set of visited paths. So we'll say visited paths includes a path. So again, we're just pretending that we have this. So we will call our own method that doesn't exist yet, get the set of paths that we've already visited, and if that includes, that doesn't include this path. So the implication here is that if we've already seen this path, we're not taking any action. This is to prevent loops. You know, if we need to, but at the very least to prevent repeated work and having multiple objects representing the same derivation. That's something that we don't want to have. So then we want to load the contents into a string. Parse that. Where do we have what we call parsing next iteration? Was here. Right, something like that. What do we do with that? So this visited paths, actually it's not going to be a set, is it? Because it's going to be a dictionary where the key is the path and the value is the paths representation. So we will make that rather derivations. Okay. And we will then say derivations at key path put so if our derivations does not include key matches the path, then we're going to put a value for that key, which will be the path's representation. And then this needs to recurse. So we visit this one, and we also visit everything that it references. So we might want to factor that out into a little other method. Let's do that. We're going to say self load derivation. So we'll load a derivation, which will have the side effect of putting it into our derivations table, and that's going to return that derivation, and then we're also gonna get the input derivation all files, shall we say, might be the same. So that's going to load one derivation, and return it and put it in the dictionary. And then we're going to get all of the inputs of that, and we're going to spider our way out through those. So this is a recursive method. That's the recursion, and it terminates because if it's already seen a path, then it doesn't go in here. It only actually processes each one once. So that is perfectly correct, obviously. And this code that we had written there, that's going to go into this load derivation method. Syntax error there. That's fine. And again, there's all this stuff in red, and we're programming in Smalltalk. There's all this stuff in red that doesn't exist. We're referencing stuff that doesn't exist, and we're going to just do this as we go. So we run this, and don't have this derivations method. We will create it. We'll make sure we have an instance variable called derivations that is initialized. So we'll say derivations if nil hasn't been initialized yet, then derivations will be the dictionary that we want. Is that what a hash table is? Yep, looks fine. It'll be a dictionary. And we will return that. Derivations will be an instance variable. So now we have a method called derivations. We also have an instance variable called derivations, and when we call this, it makes sure that that has been initialized and returns it. Fine. And now we run again in the debugger. Where are we up to now? Now load derivation we don't have, so we create that. That is going to be an updating method. I'm just pasting the little draft code that we had there. Going to take a path. It's going to So actually we want to return this, we want to put this value into the dictionary, and we want to also return it, but then kind of what's the, I'll be too fancy. Let's say put the derivation in a local variable. And we will return that derivation. Good, let's run that. Now, okay, now the problem we have is a little bit further up, that when we're testing this input derivation set, we were referencing derivation file name, and we hadn't actually initialized that anywhere. So let's see, in our next door derivation object, how do we make sure that that knows which file that came from? And this is created by that parsing method. I think we want to ever so slightly update the way that we parse things. So instead of saying this, I think we want to say nix a term parser from path and give it a string. And that's going to, we run that, it doesn't exist, that method doesn't exist. In the debugger we create it, as we always do. We create it on the nix a term parser class. And it will be an instance creation method. Just categorizing it for looking it up, finding it later. It will take a path, and it will say a path as file reference contents Hmm. Parser is a throwaway one-use object. Parses the input. And then the only other thing we do tell it what path version, won't we? May need to harmonize our names later, but for now, that's the thing. We want to load the contents of the file, parse it, and then on our parse tree, we also want to remember where it came from, which is not something you'll get out of the contents of the file. We run that again. Now we've got a file does not exist error. A path, what was a path? Okay, no, well, we did the wrong, we called on the wrong thing there. We called it on not a file name, but on the actual contents. Fine. This was a string, the actual file contents, whereas this file reference. What if we try running the same code over there? It's expecting a path and we're giving it a file reference. Probably get away with that. Let's see. And now we trying to tell the parse tree what its store derivation path is. It doesn't have a method called store derivation path, so again we just create that. An updating method. What instance variables do we have? What do we call that variable that we're trying to populate now? Hopefully it was called store derivation path, but that remains to be seen. We call the derivation file name. We're going to call it now. We're going to call it store derivation path. We might rename that. Can you rename an instance variable? Instance variable refactoring, rename. We want to rename the instance variable derivation file name. Call that derivation path. Okay, that's done. Good. Now we want to say store path will be path. Good. Now the problem is we're cheating a little bit. We're just going to hop out and uncheat. We're calling it with a file reference when it expects a path. Let's do that properly. So close that debugger. Here, instead of doing it on this file reference, we'll backtrack to the left where that came from. That was a string which was the file name. So this is a path. It's a string. Actually, what we want for input. So we run this on the string. Now what happens? Now we get a nick store derivation, and it knows where it came from. It knows the store derivation path. File reference. Okay, that's an instance variable we never used. No. Now let's do this again. Let's try to make the derivation set and see how far we get. We had a method for getting the input names. I guess that was not quite the right name. So next door derivation, what methods is there? Derivation. That I think we should just rename that. Let's do that. We will rename that from input derivation names to input derivation full paths. And we'll ask the debugger to please Try again. Debug. We will go here. This was the method call that didn't work, but maybe it will now. Okay, so now what do we get? Hang on. Pause failure. Go back to the beginning here, just for a moment. Have from the beginning. We have the file name of a Nix derivation, and what we want to do is create a set of the whole dependency tree, start rooted from there. And the way we're doing that is, first we have been parsing that file as our starting point, probably reasonable, and then we take that derivation, we say, let's get the full set of maybe that's already a little bit indirect, right? Maybe when we do it should be okay. Input derivation set, okay, so that method is not working. It's got a parse failure. How did that happen? It's loading derivation, going input derivation store parse, but that load derivation failed. The load derivation got a parse error, so we got a parse error that we didn't detect. That's something that we should fix. So the parse. We'll put a breakpoint in this method here. Because our parse has failed, and we'd like to detect that somehow. So let's put a breakpoint there, which you can just do. You can call halt on yourself. It'll pop up in the debugger. Get rid of that, and we'll run this again. I'll run our breakpoint and debug that. Here we are. What do we have here? Derivation. Okay, this succeeded. We got a full derivation. Fine. So we'll proceed a breakpoint. The breakpoint again. Okay, now we got an error. So why was that an error? The evaluator here, where we can run code in the context of this stack frame. So first of all, see if we were able to get the file contents. Did that part work? Yes. Then apparently, we managed to parse that. We now evaluate in the context of that string. Evaluates Nix from parse self on that string, which is the file contents. Fails with literal not found. Okay. Get a debug view of the parser. This is getting a bit fancy, right? So the Smalltalk debugger understands that it's a parse error and has some special support for seeing what's going on in parse errors. Doesn't completely work apparently. Yeah. What happened? Oh, which literal was not found? Could be a bug in our parser. Derive. Let's see the string. I don't quite understand how to read this, to be honest. This is some kind of a view of the parse tree. I'm gonna rather take the input if there's anything obviously suspicious there. So one thing, this is something that we skipped over a little bit, was escapes for strings. So we didn't really have a proper grammar when we were parsing these A terms, and one thing that we didn't implement was string escaping, because we just didn't know how it worked. It looks like they use the / style escaping, and this is used for several things. Okay, they also can put in new line characters, so that's actually something that we should handle in the parser. But the most critical thing is to handle the escaped quotes, because at the moment we're not actually doing anything with those strings, so it's maybe just as good to have those escapes there. But these escapes are important. Those ones are actually for A-term parser, as I understand it. /n could be in our kind of string representation. So let's go and update our parser. But I think that's the issue. I think that we're not handling string escapes properly. So let's handle string escapes properly. We parse a string. We get a quote like that. Then we say that we take anything that's not quote, but that's a bit too simple. We want to take either, put this on several lines to be a little bit clearer. So we can accept either something that's not a quote, or we can take / character. Oh, this is a string, can't we? We can take the string Now I need to worry about what the Smalltalk escape syntax is, because I don't know offhand. So if we take a Smalltalk string like that, what does that evaluate to in Smalltalk? It is a string with two items, a / and then a quote. Fine, so we don't have to escape that, the Smalltalk code. Okay, that looks a bit better. We can either take an escaped quote, parser for an escaped quote, or we can take anything that's not a quote character, and we can take any number of those. I think that we've just implemented string escaping. That's the theory. Yeah, breakpoint, we'll hop over the first one. And we have some other different. We parse this. Maybe we parsed it okay, but now we need to construct our parse tree, so let's do it. What is this? What we got? So we need to tweak this a little bit for constructing our parse tree. So I'm not quite sure if I've factored this in the best possible way. You know, we have a grammar and we have a parser coexist. The grammar just matches the syntax, and then the parser is a subclass that then constructs a suitable parse tree. But the thing here is that there we match one character, whereas here we match a string. And in that case, we want to only take second character. So really, in that case, we just want to have a quote. But another way of saying that is we take the second character, so we hop over the ape character. It's conceivable that will work. Here we are back in Here we go. We don't necessarily need this breakpoint anymore. We're going to take that out for now. Now we have a different problem. What problem do we have? Been recursing, so things are happening here. This is our full stack UI. So we say, start the input derivation set. We visit one path. We then do this do across its inputs. We visit those, recurse, and then at some point, what's on top of our stack? Derivation. Oh, that's interesting. So we have here some kind of a special built-in, which is not something we counted on. Have a special built-in, doesn't seem to have any inputs, is that right? Let's look at this. Stuck somehow. Okay, so this, the built-in fetch URL, we didn't get any input derivations. Is this something with our parse, or do we parse an empty list nil instead of making an empty array or something like that? Be a bit. Let's make sure that when we parse a list, we get nil out the other end. I think that's a problem in constructing our parse tree. That would be nil, then replace it with an. It's plausible. Go back up the stack where we were. Restart here. So we just clipped the stack back up, so we kind of threw and caught an exception ourselves. Put us back in the execution state we want to be in, and now we're proceeding there. Oh wow, we got something out the other end. We got derivations, which is a dictionary. A lot of entry. Lib SSH, lib elf, lang, gawk, lib XML, Perl XML parser. We got a lot of stuff. So I think that this is the transitive closure of all the dependencies that we need to run a Raptorjit script. So it's everything that, the script needs Raptorjit. Raptorjit needs to get built, and it needs, at some point we're going to need a compiler, we're going to need a libc, and any tool that we use along the way, like we need to be able to build GCC, so we need all the dependencies for building GCC, and it all goes out. So this is the flat view. So this is progress, right? This is the flat view of what all our dependencies are, and what we need now is the structure. I want to see how these fit together, and it's actually, I think it's quite interesting that there's 228 total software packages involved in running a Raptorjit script from scratch if you were going to build everything from libc and kind of GCC and whatever upwards. So this is the kind of the raw view. Cool. So we're gonna take 5 minutes break, and we're gonna come back, and we're gonna turn this from a list into into a graph and make that visual in one or two ways. Pardon me while I run my little script, and we are back in 5 minutes. See you then. So back again. We had just taken kind of got the busy work out of the way, where we are now taking the name of a Nix store derivation, and in order to calculate the kind of the transitive closure of all of its dependencies, we're going out to the file system, reading its derivation file, parsing that, finding all of the inputs, and then recursing through those, and we're constructing a set which contains one object for each derivation, and that's what we just got. So we hop over to the code again. That's exactly what we just got. So this is now a little overwhelming. There's 228 objects. There's patch-elf, there's libreadline, there's bin-utils, there's a Lua script. There's a lot of stuff here. So what we want to do now is get the structure of this. So what we really want to do this, we're going to use a Smalltalk visualization toolkit. I'll pull that up briefly, called the Agile visualization framework, which is awesome. Again, this is the reason that Studio is written in Smalltalk for the front end is because basically of a couple of really nice visualization, or kind of a really nice object inspector called the Glamorous Inspector, and a really nice visualization library called Agile Visual. So this is basically just catchy-fies, a way to construct object graphs, to visualize graphs in different ways that are kind of convenient. A bit short. Just show a couple of screenshots briefly to see where we're going here. A bit too simple. Take objects and they represent them as rectangles, and represent them rather as words, which might be what we want to do. We might want to use the name of a derivation to represent it, and then they got some edges there. You can connect the edges in different ways. So here, each object, they're showing a lot of objects, so they're not using labels. They're just representing each one as a small circle, and they're showing the edges in a kind of a very stylized way. There's a lot of different ways that you can do that. You can represent an object. You always map an object onto some visual aesthetic, and then there's a lot of ways that you can visualize, that you can show that aesthetic. It can be text, it can be a box, it can be a shape, and then there's a lot of different ways that you can connect them, different kinds of lines, and then there are a lot of ways you can do layouts. Like here is a bit of a strict tree layout, and we might want something a little bit like a tree layout ourselves, because the dependency graph, it's a directed graph anyway, and it's a bit ordered. So there's a lot of things to choose from, and it's going to be really easy to experiment with these, I hope. That's the idea. So let's do this. So to use this library, we need to do a tiny bit more legwork, because it wants us to give two things. It wants us to give us like nodes and edges, and we have the nodes now. So we hop back here. We have our 228 nodes in the dependency graph, showing how you run a wrap-digit program with Nix. But we need to also get the edges here. So we're going to add another method here that returns a set of associations, key value associations, with the dependency from the key to the value, and that should be reasonably straightforward. Let's see. So this object here, what was it? Is a Nix store derivation set. So we're going to have two methods. Derivations, does that already exist? Yes, that is the set, that's the nodes. And then we're going to add another method called dependencies. That doesn't exist, we just called it, and it doesn't exist, but we're programming in Smalltalk, so that's normal. We want to create it now. It's going to be there, and it is going to be an accessing method. We're going to construct that. So it's going to be a set of associations, or a list, we'll say. It's going to local variable. And we're going to map across each of our self derivations do. So for each derivation that we have, we are going to then map across its inputs. Me just writing a little bit of code quietly. So the point here is just that once we get a store derivation object, we can ask it what its inputs are called, and then we need to translate those names into derivation objects, and they need to be, the identity of those objects needs to be kind of matched. We want everything to be the same objects that we have in this set. That makes sense. Let's see what we got there. Okay, so now I call self dependencies, and we got an ordered collection of 857 items. So our 228 nodes have now expanded out into 857 edges, and each edge has a key and a value. So our it's a bit of a pain that it just says anix store derivation. It would be kind of neat if that was a little bit more meaningful. So let's do that as the next step. Let's get a method to make the store derivations print in a nicer way. We will give that a called print on, and actually I take this opportunity to shorten the names a little bit because you know, derivation store name is long. If we grab the example, store derivation filters. That's a little bit suspicious that we don't have a store derivation path there. But anyway, one thing. So that's the thing that it builds. But this name is just a bit long, right? So I think we would be happy to have that part. And if there was a .drv at the end as well, we'd probably want to skip that. So I think we want to shorten the string a little bit. So the question then is, how do you do string substitutions way in Smalltalk? And just thinking about it, is like, what's our tool of choice here? Do we want regular expressions or what? I think regexes would be kind of nice, actually. A simple formulation that I think would work, for now at least, would be to just kill everything up to the first hyphen, right? Because I think that all Nix expressions have this structure. Maybe not in principle, but in practice, I think it will always be Nix store. What's an easy way to just drop from a string everything until the first hyphen? I'm programming in Smalltalk all the time, so I often have to look up these kind of basic things like string library thing. That's fine. One way that we could do it, trim off everything that's not a hyphen, and then drop the hyphen. Let's see if there's anything slightly more correct. Oh wow! You know, we could do this in such a simple way, couldn't we? Again, this is maybe not really future-proof, but if actually, I'm happy enough with this for now. It's a bit cheeky. Sorry, where were we? It's not looking quite right. I'm just trying to chop off a fixed number of characters, so we know we're just being a bit cheeky and we're saying that the length of the prefix is always this, prefix len, so we just want to drop that. But I seem to have got it slightly wrong. Now we just drop a fixed number of characters from the start of a string. Back here where we were. Copy from 2. What do we really have derivation? Wrong. Variable called. That's my derivation store. Derivation path. Again, we want to make a short. Well, summarizing, we want to get a short name for this store derivation object. The way we're going to do that is take the store derivation path for the class. And we're going to copy from after the fixed length prefix, which might be an issue if we end up with different paths, so I don't think that happens actually in practice. It's incredibly exotic. Store derivation path. And we're going to also drop the .drv if we have it. Actually. We'll just ignore if we don't have that, I believe. So, we gotta get a short name. Well, let's just see if this whole thing works now. So what we've just done, really basic thing, on our next door derivation, we made a method printed on a stream, and does that by just printing short name, and the short name is just stripping off the prefix and the suffix file. Anyway, let's try again. Where were we? Where did we start? I closed our inspector. Open another one. Was it auto workspace? This expression that we started from. That again. Got a string which is a store path. And delete that. Now you know what? There's another thing that I just noticed in passing. Totally breaking the flow. We need to change the way that we do the parsing. We added a method for creating store derivations. We didn't update all of the callers, so we're going to do that now. See if this works. We'll do a dive in, store derivation, and actually want to see references to this class. There, that findable here, little search engine. References, yes, that's so fantastic. This is an amazing environment actually once we get the hang of it. So I searched for a class, and now I'm searching for every reference to that class. Is that finding what I want? Hold on. Where did we... Yeah, where was our derivations set? I don't think I did find it. Take back everything. Derivation. Okay, this is what we changed. Now it's not that. Now it's we created a method that on path. Okay, fine. We want to write this, and that is to make sure that the path instance variable gets initialized. And now Okay. Then we have a string, which is a derivation path. Take this one instead. We want to now parse that and make a dependency set. Programming takes a while sometimes, right? But anyway, we persevere. Now we want to take that file name and we want to say keep that there for a sec. Next, store derivation from path self, which is that string. This should give us a store derivation. We need to create an instance and call that, I suppose. Why not? That path. Interesting. I think we're calling some code that we weren't calling before at all. Hold on. This is not how we created it before, and I don't have that in front of me, so let's might have some kind of overlapping code to do the same. We're just going along now. That actually gave us something more like what we want. We have next door derivation object code. Now we should be able to make an input derivation set of that. Error. File not exist. Okay, this is a problem we've had before, is it not? We are at some point we are trying to use the contents where we're supposed to just give the path. But, the path is wrong there. Load derivation. That's just wrong. Path there. Is that if we live by the debugger, we die by the debugger. We do a lot of coding in the debugger, and we end up back there when we screw things up. Anyway, we've got a next store derivation set object. We say self derivations, then we get 228 items. The key here is the path value is actually an object, where we're now printing those objects in a pretty way, so those are actually derivation objects. And if we ask for the dependencies, then we get the edges. This is starting to look more like what we want to see. We see that libelf depends on bootstrap tools. We see that libelf depends on the source tarball for libelf. This actually looks pretty plausible. So that's nice. So now we actually finally have something that we could try to visualize. So let's do that. And it's only 800 items, so we'll try doing this just as a graph to start with. For this toolkit, there's a new version of this, Mondrian 2. Search that with Pharo. I don't know. Okay. We'll just use the one that we saw documented there. let's first just copy paste one of the examples to make sure that we actually have this installed. We're going to paste that. Got it? What are we doing? We're creating a Mondrian, which is an object for creating visualizations. So its nodes will be these strings. We return that. What does that get us? That gets us 6 boxes. If we do a mouse over, we see what those boxes are. Nice. I think it might also be possible to say that they should be text. Yes. Then I think we can say something like b edges. Yeah, hello depends on world, like this. Maybe? No? Not edges. What is it called? No? Associations. Then we get hello and world depending on each other. Nice. Then we should be able to say something like the layout 3. Yes, okay, so we're going to do a script something like this. Instead of working on those strings, we will work on our other stuff. So let's copy paste this over where we are working. Here. So this is going to become a method on this dependency set to do a visualization. But for now, we will create the Mondrian visualization builder. We will tell it to represent nodes X. The nodes will actually be at the moment our derivations. Okay, so derivations returns actually. What is the type that we return from derivations? Go down here for a second. Gives us a dictionary. Okay. We actually want the values, which are those. Which are the derivation objects. What about if we just start with that actually? I just comment out. The line can go. We don't want that example. Comment out those. Would this give us? Okay, then we have a little visualization with just each of our derivations represented like that, which is nice. This out of the way. So let's give that some edges. I'm going to say B edges use associations, and there we have. What was that code that I just deleted? Self C's. Okay, now we have. Now we just got to find a layout that works. So if we try a tree layout, let's see what that looks like. Nasty, right? Work at all. In. How do we get so many? Doesn't that look slightly suspicious to have so many edges? Yeah, we're expecting to have 857 edges. It looked like we had more than that, but I'm not sure. Maybe tree is really bad. What else do we have? cluster layout. Let us try. Okay, that looks still big though, right? Wow. I don't know if this is actually the data or if something's gone wrong. Let's go and try another couple of layouts and see if we can put it in a way that actually makes sense to us. Try doing something that looks more like this. Okay, don't use the edges in the layout. Oh. Okay. How many edges do we have there? I don't know at this stage whether it's just a messy, whether the real picture is messy or whether it's become messy something rendering. Let's try another couple of layouts. See if we find anything. We take a dominance tree. And we do want to use the edges in the layout. Yes. Question is, does this make sense? So, fragment. The Perl, depending on the Perl sources, use the Perl, look, I'll get text, depending on Perl, and I'll get text, so that little fragment looks okay. So maybe it's just a messy picture. I would actually love to think about what is a good layout at situations like this where you don't care about it being neat, you just want to kind of see whether the anatomy is about right. Like, do you have the right number of nodes and the right number of edges? Try another couple of layouts and see if we can do anything. What's something called a radial tree? Layouts. Radial tree seems to work. Stuck, might be too complex. Try a cluster again. We can use Bezier curves to the effect. Let's see. That's going to stuck, so we interrupt that. Fine. We're going to go with a cluster layout. These ones again are going to be not in out. So that's the best layout we've got so far. Let's see if we can get those other curves and stuff. Edge builder. There is an edge builder object. Ash. I want to see if there's just a simpler variant of that method. Pharo. Give it a try. It's not entirely legible, is it? Doesn't have long name. There probably are only hundreds of them, right? Like probably. Can those edges be right? Such a lot of edges. What about if we try it on a simpler example? What about if we... Now we did RaptorJet, which depends on a lot of things, so what about if we try and do it on a simpler example? See if that gives us a better idea. What about if we look at the dependency set just for bash? Let's cheat. Let us say... We don't even have to be like that, do we? We just want to find another derivation to use as a starting point. Where's a simple one? Use it. How complex can it be? What is derivations? 55? Is that going to be more manageable? Okay. Now let's see if we can use the edges for layout. Maybe the cluster layout is not the best. Maybe now we get away with a tree layout. Not a radial tree. Facing. There are quite some, right? Why don't we take an even simpler example if we can? That'd be what about if we look at GCC instead? And actually now, you know, the funny thing is, that's an object representing GCC, so if I just click on that, then I'm getting an object here. So we can just walk our way along like that actually. There's still 50 items here. There might be, it might well be that these dependency graphs just don't get that small in general. So it might also be that this is the wrong approach. I think that's the message that I'm getting here is the dependency graphs are pretty big. So you don't really want to be necessarily putting them all on the screen at once, at least like this. It might just be there's a little bit too much information there, and it might also be that a lot of the information is kind of irrelevant. We might only care about the nearest couple of dependencies, whereas now when we go all the way into seeing kind of how the whole system is bootstrapped, which is kind of interesting, like, well, what are we getting here? We're seeing how GCC itself gets built, I guess, depending on Bison, zlib, glibc, busybox. I mean, I guess that we're getting a view of the kind of the beginning of the Nix universe here. Can that be right? When we say we want GCC and it says, well, in order to build GCC, we need to build all of this stuff. To build GCC, you need the GCC sources. You need tech info because you're going to be building documentation for GCC. You need Linux, you need Perl, for some reason, possibly. Why do you need Perl? We should be able to see there. Something there is depending on Perl. It might be tech info. Okay, cool. So this is not actually the answer I wanted, but it's an interesting answer. Well, it's one of those be careful what you wish for situations, right? So I wanted to see the transitive closure of all dependencies for anything, and the answer seems to be that there's a lot of them. So this is actually fine. I don't think that this is useful. We might be able to come back to a visualization like this and just pare it down a little bit. But I think if we switch to a tree view, we just kind of click on things that we're interested in, then I think we'll actually be on the right track. So for now, it just looks like the dependency tree is a bit too intense, and probably there's probably massively diminishing returns for expanding out this tree, right? We don't actually care how the compiler got bootstrapped, even though it's very interesting actually to know that that's there. And on a Sunday afternoon, it might be interesting to browse this and actually kind of understand how the whole Nix environment bootstraps. But generally, we don't care about that, right? Generally, we're interested in just stuff that we're actually building and that kind of is sufficiently close to whatever it is we're doing. Like if we're running a wrap-digit program, we're interested in seeing that run, and if the wrap-digit VM needs to get built, we want to see that, and so on. But we don't really care about how the compiler was bootstrapped and all of that. So let us stop for 5 minutes again, and then continue straight on and put this into a table tree, an expandable table, which I think will be a better view for us, and something that we can really work with. So we're coming back soon then. So let's dive back in. Now, just to recap briefly, what we're doing is making our Pharo UI in Studio be able to understand the Nix store, and specifically to be able to take the name or a description of something that should get built by Nix on the back end, and to make a dependency graph out of that, and to be able to then see everything that's involved in producing that artifact. You know, if we want to run a program, we should see the compiler that's needed, the virtual machine that's needed, and everything. We want to be able to then visualize that, and we're maybe stepping towards being able to see the kind of status of each of those things. So if what we really like is be able to kick off a build and then have a kind of X-ray vision onto the Nix store to see everything about the build, everything that's in progress, everything that's waiting, and that kind of thing, just always to know what's going on. And what we've done now is to make this graph visualization. We just found that if we take the transitive closure of the dependencies and plot them in a graph, then it's too big and it's too confusing. So we're just going to take a step back and do it in a tree view instead. So let's just do that. We have an object of class Nix store derivation set representing a set of derivations and their dependencies, and we're going to extend this inspector. We're just going to add a tab right here. So now we've got a couple of ways to inspect this object as a Smalltalk object, but we're going to add here a way to see the Nix level information. So the way that we do that is, we don't really need any of that, but we'll just keep it there for the moment. If we browse the code for this object, then we want to add a method called inspector derivations in opposite. What are we going to do? Is that the simplest thing that could possibly work? Let's see. How about that? If we refresh now, yeah, now we've got a new tab, which is what we wanted, derivations. And okay, we haven't got any columns in our table, so we've got all the items. So I guess if I click on one of these, well, it wasn't so happy. Anyway, we need to have some columns. So let's add those. How about now? Oh, we don't have any as children. For now, we said that we were doing a tree, but we didn't say how to find the children, so we'll just punt on that for the moment. Say, for the moment they don't have children. Where were we? Yeah. But if we refresh now, work. Oh. Seems like it's wedged. What's going on? Cool. Inspector is not so happy. Get rid of that. Find one of these. Find all of these objects from the heap. One. Okay, that's our table. So pardon me. This is a bit small talk. I lost the object I was interested in, so I just said, for the class that I'm interested in, give me an array of all the instances of that class, and it just scans the whole heap and just produces that array, which is actually really kind of convenient. Very small talky. So there are 3 of those derivation sets that we've created just while we were mucking around. If I expand this a bit. Well, take this one. Okay, so now this is the table that we defined. Now what we want to do is to be able to actually expand this. We want to actually have children of these. So how do we do that? We're going to say, we want to check if something has children. We just said that they never have children, so let's change that. Let's say, we're going to look in the take the dependencies. We're going to filter the dependencies is an array of associations from a derivation to something that it depends on. So if an object appears as a key in the dependency table, then it has children. It depends on something. So let's write it like this. If the self-dependencies detect an association where the association key is this derivation. No, it's not detect, is it? We want something returns true or false. Detect is how you actually find an object. That's not what we want. Closely related. Any satisfy. That'll do. Is there any dependency that has this object as a key? In which, if so, it should have children. If that gives us anything. Refresh this. Yeah. Sure that it looks a little bit suspicious. Why does this not have dependencies? It doesn't look like anything kind of primitive, but oh no, sorry, that is a primitive because that's a source tarball. That's just a tarball that was fetched, so that actually does make sense. This tarball doesn't have any dependencies because it's source code tarball. Actually, the build, which we'll find somewhere else, does. Good. Okay, so that's one step. Now we say which ones have got dependencies. The next things that we want to do. The next things we want to do are to be able to click on these arrows and expand them. I guess something bad happens. We get an error if that happens now. And then we also want to root this on just one place. We don't want to have this kind of flat. We want to have just a smaller starting point. So we'll do that in 2 steps. First step then, we go children. Select all the association. Select. And collect. select, then collect. We have a predicate saying which objects we're interested in, and then we have what we want from those objects. So that we've got some associations. We're interested in the associations whose key is this derivation, and we're then interested in the value of those associations. So we're going to find all the dependencies. See if that can possibly have worked. Refresh this. Yeah. That's a little bit more manageable, right? BusyBox seems to be a primitive, isn't it? It's interesting anyway to be able to see this. This is looking much better now. The only thing is that we have everything. We have all the stuff listed at the top. We want to filter that down. Actually, on these derivation sets, we probably want to remember where they start from. We do want to do that. We create this again. At some point we're doing that. Suppose it was in store derivation. Yeah, so this is where we create that. So when we create one of these store derivation sets, we actually want to, I think we want to remember where it started. Why don't we make a method for doing exactly that? If we just say x store derivation set start. Of try that. And that's a method that doesn't exist, but we'll just create it up. So let's run that. Derivation path stack. Run. Just run that from a shell somewhere. We just fine. Need a string there, which will be derivation. Get it from anywhere, you know. There's one. Copy and paste it out of this Emacs buffer we had lying around. Bash. Run that. Get a debugger. Let's meet method. Derivation class. Instance. Creation category. Run that. Tell us that starting path doesn't exist. Add that. Access. An instance variable. using a lot of memory, which seems suspicious. Let us debug. How do we get into an out of memory situation? Get a string. How big it was. Huge string. That happen? Oh, okay. That's something a bit random looking. So I gave it a bad value to test on. I wanted to give it the name of a derivation. I gave it the name of a package. Somehow something went wrong when it tried to read directory, I guess, or maybe it was bash itself. I don't know. Anyway, but for now, file does not. So derivation exists. Agile scheme. Is there any? Like that. What do we have? Oh, we got the wrong object. Miscreated method. Starting a path, but we did not return the object that we create. Should have. So we'll try that again. Now we still see the same view that we saw. We can expand things, and that is nice. And what we hope now, yeah, we know what our starting path is anyway, so we should be able to then update our update this to actually get the thing that we want. So instead of just this one, I'm going to say one element, self derivation for path. Maybe the starting path. That's at least worth a try. That's better, right? So we were interested in, we asked it to show us the dependencies for Agile scheme. And it certainly looks like that's what we're getting here, right? That's reasonably cool. I would like to, when this opens, and what I want to do now, this is actually quite nice, right? So now this is a lot of what we wanted. We say that we want to do something. And we want to know what Nix would do to build Agile scheme in this case, and it tells us, in order to build Agile scheme, I would need to first build curl, the mirror list, standard environment, and bash. Okay, well, to build curl, what do you need? I need libssh, I need zlib, OpenSSL, I need the curl source code tarball, I need Perl, a lot of stuff. So, and then to build Perl, what do you need? Okay, I need GCC. What do you need to build GCC? So it's actually pretty interesting, I think. And of course, normally, well, one more thing that we're very interested in, I don't know if we'll have time to do right now, is to say for these things, is this something that's already built, or is this something we need to go and do? So of course, if we would really need to go out and build all these things, it would take all day. But you know, presumably these things are already present, or even if we don't have them present, we can go and fetch them as a binary. Anyway, let's just take a couple of more little steps, and then it's actually time for lunch. So anyway, we're actually in a pretty satisfying place right now, actually. So it's been a long slog to get here. We only have the very beginning of what we want. I think we're just going to do one tiny little step to feel good, which is going to expand that tree out a little bit more from the beginning. How do we do that? Fast tree table. For an example, examples of where that is called. Anything, yeah, expand, okay, expand it until 1. Try that. But if we would start that again, see what do we get. Look. That's more expanded than I would have guessed. What does expanded to 0 do? That's more like it. That's the kind of view I would like to see. So, this is a satisfying step. So the idea, in my mind now, going way back to kind of what the initial idea was, if we're in Studio and we want to build something, we want to run a Raptorjet program, we want to do anything that's going to produce data for us to see, when we kick off a build, I would like to see something like this, showing everything that's relevant, and I would probably want to expand this out to cover everything that is not already ready and cached. So, for example, if Guile needed to be built, then this would be expanded. If curl did not need to be built, it wouldn't be expanded, whatever. And then in real time, I would like to have this update and show us what is currently building or downloading, and if we click on that, we should be able to see like the real-time log of whatever is going on with that package. And then over time, this will all collapse down until we just have kind of our top-level thing there. That's the direction that I want to take this in. But you know, we can't go too far down this hole right now. This is a reasonably satisfying point. Let's stop there for now and continue this another time. Thanks very much for watching my stream.